All right, here we go. So yesterday we left off talking about polynomials, right? And we said we added a couple additional points that the notes didn't really cover. So we said a polynomial is going to be a sum of terms, and each term is going to look like a coefficient times the power of x, right? Just a quick reminder, because this is where we kind of got cut off. The exponent has to be a whole number for it to be a polynomial, and the coefficients just need to be real. They just can't have any i's in it. They can't be complex numbers with imaginary parts. Could you potentially have polynomials like that? Yes, but that would fall under the umbrella of a real or a complex analysis class, and we're not doing that, right? That's something you'll do in college. So, standard form is we're going to write the exponents in decreasing order. Now here is one thing that a lot of textbooks don't cover that this worksheet does. So what is the degree of a polynomial again? Highest exponent, okay. What if a term in a polynomial has more than one variable in it? Okay, let's do this one first, just to kind of warm up. If we wanted to write this in standard form, what would it be? Okay, negative k to the fifth. Okay, and then we have cubed, good, plus okay, so what's the power of k here? 5, there it's 3, there it's 2. What's the power of k there?
1.
What's the power of k there? 0. Yeah, there's invisible k to the 0, isn't there? Right. Okay, so that's in standard form. Another thing that this worksheet doesn't really go into, but what is, like if we take, for example, this polynomial right here, what's the leading term? Anyone want to guess? I think I've mentioned this. What's the leading term of this polynomial? Negative k to the fifth, right? So the leading term is going to be the term with the biggest power of x. That's simple, okay? And how many terms are there in this polynomial? How many? 5, right? Because terms are things in math that are added or subtracted, right? Okay, there's 5 terms that are added up here. Okay, so leading term is the term biggest power of x or whatever the variable is, right? Biggest power of the variable. It could even be plural, okay? So that's the leading term. What's the leading coefficient? Yes. That's just the coefficient in the leading term. Yes, sir?
My question is, so if you had multiple different variables, would you do greatest power per variable, and then so would you like do one variable and then do the next variable, or would you still just do greatest power of least power?
Good question. What do you think here? I'll let you guys tell me what your intuition tells you, and I'll tell you if you're right or wrong. But what do you think the leading term is? Alphabetical?
I have no idea.
Okay. I mean, it's.
Oh, wait,
that's
no,
seems
it's
reasonable.
not.
Yeah.
Yeah,
Both coefficients biggest next.
Well, so like,
Biggest
yeah.
Okay, biggest exponent to least exponent. But how are you going to do that if I've got an a squared, b squared here, but then I've got a b squared here and an a cubed here? Which one goes first? Okay, a cubed goes first because it's the biggest power of the first alphabetical variable, maybe, right?
Yeah.
That seems reasonable. That's not how we do it, but that seems reasonable.
Right.
This is
biggest power?
this is the leading term. Can you tell me why? Okay, but I could have, like, what if I had even if I had, if I added the term plus 20 A times B times C, that still wouldn't be the biggest.
It's got the
A
most
squared.
eggs
Ah, there you go.
Yeah.
Okay, so the sum of the exponents, right? The sum of the exponents is
You don't know
gonna
how
give
to-
you the power. Okay.
No.
So this guy would go first.
You don't know how to say.
What would go second? A cubed. Okay, now what if though, here's another thing, this didn't come up here, but what if you had, oh, it'll come up the next one, never mind. Yeah, okay, this is good. What's next? Ah, okay, yeah, look here, it comes up here actually. So I've got my plus 4a cubed. Now each of these terms has a degree of 2, don't they?
Yeah.
Okay, which one do you think you'd put first?
AB.
A, B, then you go alphabetical. Okay, so we're gonna go plus 7AB minus B squared. And if we had an A squared term, that would come in front of the AB, because A times A is alphabetically ahead of A times B, right? Make sense? So what's the bottom one gonna be then? 9x cubed y minus y to the 4th. They're both degrees of 4, but this one's alphabetically ahead of it, right? Okay. Yep. There you go. There you go. Right? Because that's got a degree of 4, degree of 4, degree of 3, degree of 2, degree of 0, right? Okay. Is that a big deal? No, not really. How often this year are we going to deal with polynomials like this? Today. I mean, that's it. We're interested, what we're really interested in an Algebra 2 class are useful polynomials to us, and those are going to be polynomials that have a single variable in them. So either all x's or all z's or all y's or something like that. Yes, sir.
So what if you had like a squared b to the b cubed, and then you had like a cubed b squared? Would it be the one with a cubed?
Yeah, the one with the most a's would be,
All right.
yeah, so here's how you can think of it. Like if you're going to put them in order, you would you'd say which one, if I lined them all up, like this has got a degree of 4 and that's got a degree of 4. But this has got more x's than this one does. See what I'm saying? Okay. All right, so now let's practice. We're going to classify polynomials. Okay, there's 2 ways, and this is, once again, this is something you learn in an Algebra 2 class, and you got to be able to, you have to be familiar with this so you don't sound like a doofus when you go to college. But you really, it's not like this is that big a deal. This is just something, it's going to make you sound really smart when you're talking about polynomials. But it doesn't really give you a lot of extra information, right? So we classify polynomials by degree and by number of terms. And when we classify polynomials, think about other things you've classified in math. You classified, for example, quadrilaterals in geometry, right? How would you classify quadrilaterals? Well, give me an example. If we were going to talk about quadrilaterals, what could you do? Okay, you could, if you had 2 sets of parallel sides, what kind of a quadrilateral is that? Well, but yes, but you know, that's more specific than necessary. If I've got 2 pairs of parallel sides in a rectangle. Okay, but not trapezoid. Trapezoid's only got 1 pair of parallel sides. So now think about this. A square is, okay, here's an analogy. It'd be like saying, how do you classify soft drinks? And if you said cola. Okay, well, colas, there are other soft drinks other than colas, right? So cola's too specific. Is there I want the broadest, the most general category of quadrilaterals that contains 2 pairs of parallel sides. Parallelogram. So that's the definition of, that's how we categorize by the number of parallel sides. You have a parallelogram or you have a non-parallelogram, right? Okay, so now what else could you do? You could also classify by the, what else? Give me another criteria. Okay, you could say the length of the sides. What if all 4 sides in a quadrilateral were congruent?
It's a
Square.
Okay, that doesn't have to be a square though, that's too specific.
Rhombus.
It's a rhombus.
What?
Okay, that's the definition of a rhombus, it's a quadrilateral with 4 congruent sides, okay? So then, okay, so how about this one? Yeah, what if you had right angles? What if you had all right angles?
Rectangle.
Then that's a rectangle, right?
No.
Okay, so then what is a square? It's a rectangle, but it's more than a rectangle.
Rectangle and equilateral.
It's a rhombus and a rectangle, right?
Yeah.
See what I'm saying?
Oh, God.
So it's an intersection of the two.
Just go on this.
Go on.
Just rhombus, there you go. Okay, so we're gonna do the same kind of thing here. We're gonna classify polynomials by 2 things. We're gonna classify by degree and by number of terms. You could probably tell me what some of these are without even, you know some of these. What do you suppose I call a 0th degree polynomial? That's the power, the largest power of x. So if the largest power of x is x to the 0, what's that gonna look like? Like 11x to the 0 would be equal to what?
11.
11, right?
Yeah.
Because x to the 0 is equal to 1.
Oh, yeah.
So what do you think I could call that then? What would I call a 0th degree polynomial?
Okay, that's
Wait,
not any
what are
problem.
like, what are first examples of words? Yeah, give us a, what are the part?
Okay, so, well, now think about the difference here. Like if I gave you some things and I said x versus y versus z versus 3.
3.
How is 3, what is 3 that's different?
An integer.
Okay, it's an integer, but what if it's 3 halves then?
Real number.
Or pi?
Real number.
What's different about
Wait.
those?
Okay, that was non-imaginary.
Okay, those are all true.
But
If the variable is removed, right, because the variable is to the 0th power, so it's equal to 1. So the variable doesn't show up. What's kind of the opposite of a variable?
a constant.
A constant. There you go.
I know that one. Fair noble.
Okay, so a 0th degree polynomial is, would you ever think about it that way? Very seldom, right? We've talked about constants a lot, but we've never once mentioned that they're a 0th degree polynomial. Okay, do you very often do that? No, you don't. But it does fit the pattern. So a polynomial with a degree of 0 is always going to be a constant. Well, what about a polynomial with a degree of 1? Now think what this is going to have to look like. Polynomials, the powers have to be whole numbers, right? So if the biggest power is 1, there's only room for one other power, which is 0, right? So what would I call that? Can anybody see an example up here of a first, which one? 13, yeah. Okay, what does that look like? One variable, and it's to the first power. What do we call those kinds of functions? What is it? Linear. There you go. Right? It's linear. Okay? A first degree polynomial is a linear function. Okay? Now okay, we can move down the line. What do you think a second degree polynomial is going to be? You see an example up here.
17.
17, what's that? Quadratic. There you go.
A
parabola.
parabola.
Okay, what's a third degree polynomial going to be?
16.
It's going to be like 16.
And that's, you got what I the numbers.
A non-linear function.
We just did this.
We've talked about it.
Wait,
Barely in
is
here.
it the little one? Oh, wait, never mind.
Yeah, yeah, it's going to look like kind of like an S, right? It goes like that.
Oh.
I don't like this.
For you guys, it looked like
Oh,
that.
wait.
But what is, and we've talked about them. When we did our remember we did our toolkit of all our parent graphs?
Yeah, I do remember.
I know, I know.
Yeah.
I don't even know what it is.
Cubic.
Cube.
That one's a circle. I told you.
Okay. Now, what about a fourth degree polynomial?
One.
Is that the one that
Okay,
gets
this
like
is one.
forever close?
Yeah, we can look at the.
Quartic.
It's quartic, yep.
Actually,
I saw that
In
on
fifth degree?
Instagram.
Okay.
Quinn? You, okay.
Quinton.
Can we see the quarter formula?
Okay, so then we can start to categorize these, right? We can categorize these by degree. So the first one is linear, right? Second one is, no?
Cubic.
Now, hold it. So now you're confusing the number of terms. This is the degree, right? It's the degree. It's the biggest power of x. 24 is cubic.
Quartic.
Okay, but we can do more than that. We can also classify by the number of terms, and these are ones you're probably going to know. You're going to know these. So a one-term polynomial is called what? Oh.
Whoa. Relax. Mono. Five. Second one's binomial.
It wasn't.
Quadromial.
Yeah, and so, I mean, we could keep going, but I don't even know what they'd be called. For 4 or more, we just give it, we just call it polynomial, meaning many terms. So let's finish naming this. What is it? This is a linear.
Linear binomial.
What's this?
Trinomial. Monomial.
Constant monomial.
Cubic polynomial.
Cubic polynomial. Quadratic trinomial.
And then monomial.
Quartic monomial. So, give me an example. Somebody raise your hand out here. Let's get some contributors. Give me an example of a cubic binomial. Okay, yes ma'am.
6x cubed plus 3x.
There you go. Okay. Give me an example of a linear monomial. Yes, sir.
Could you do 6x cubed plus 3?
Yeah.
You have to-
Yeah.
Sure. Could be 6x cubed plus 3, could be 6x cubed minus
As
1.
long as
just
it's
be
x
It's
cubed.
6x.
Yeah.
Yeah, just, so it, right, the cubic part is, let's color code this. So the cubic part is that, and the binomial part is 2 of those, right, 2 terms. Okay, what's an example of a linear monomial? X. Okay, let's make it more exciting.
4000x.
There you go, right? Okay, it's got to have an x to the 1 in it, it's got 1 term. Okay, good. All right, so next issue. Want me to go back? You good? Okay. All right, so now we're going to get into arithmetic with polynomials, right? Now think about, now what's this going to, it's going to gradually, if you think about arithmetic with numbers, adding and subtracting is pretty easy, multiplying is a little bit harder, and dividing is even a little bit harder than that, right? Same thing with polynomials. Okay, so adding and subtracting polynomials, really simple. You've done this before, you know what to do, we'll just review this. What do I do if I'm adding polynomials? Add like terms, that's it, right? All I do is add like terms. Okay, so in this case, we would, if we combine like terms, now notice these polynomials are not necessarily written in standard form to begin with. Of course, we want to write our answer in standard form, and Moodle will expect you to do that too. So what's going to be the degree of my polynomial here that I get when I find this sum? Squared. Because the biggest power in either polynomial is 2, right? So if I add up, whoops, wrong one. If I add up like terms, what do I get? 4x squared. Okay, then I got my x's. So I got 11x minus 5x. 6x, good. And then finally I've got plus 4 minus 13. There we go, right? Okay, escaped. Now, what if, and I can do the same thing here. What's the only difference here? Very little. I'm just gonna have only one n cubed term, right? So it's gonna start off with 9n cubed and a bunch of other stuff, right? Okay, what about subtracting? What's the only difference in subtracting? You distribute the negative. Now, I'm gonna urge you to do that. I think if people, in my experience, if people try to do this by subtracting each time, they're gonna get messed up. It's easier, if you really wanna make sure you're not making a mistake, it's easier to just distribute the negatives and add like terms. Okay, so then this one would just become 5k cubed minus 2k squared plus 2k. And if I distribute that negative all the way through, what am I gonna get?
0.
Minus
Wait, I love you talking about that.
2k squared
Minus 2.
minus 2k minus 17. So once again, if I just add up like terms, I've only got one k cubed term, right?
Yeah.
So I get 5k cubed. Now look at this. 2k squared, or negative 2k squared, oops, never mind. Those add, don't they? Okay, so I'm getting negative 2k squared minus 2k squared is how many k squares? Okay, what about this one I've got? 2k minus 2k cancels. Okay. This is what we call horizontal cancellation. They cancel to 0, right? This is different than vertical cancellation, isn't it? Like if I divide x by x, what's that equal to? 1. Okay, so vertical cancellation, things cancel to 1. Horizontal cancellation, they cancel to 0, right? And then finally, I just get one other term remaining, minus 17. Okay? No big deal. Okay, we can all do that. Okay, we can skip through that stuff. What about multiplying? And you've done this, right? Multiplying's not hard. You gotta be careful when you're multiplying. Yeah, what happens with multiplying? Okay, yeah, we're gonna distribute, like if we wanna do, here, let's just do this one. And maybe that one. Okay, so what if we do this guy here? What are we gonna do? Let's talk about this.
Don't you just distribute?
Okay, and when we say FOIL, what you really mean by FOIL, because you might have learned this in Algebra 1 maybe, you might have learned this as the FOIL pattern, which is first, outer, inner, last, right? Did you learn it that way?
I don't remember.
I mean, that's what FOIL stands for.
I didn't.
Call that word.
Okay, and we just call it foiling, but really what we should do with foiling now, because we're moving on to bigger polynomials, is just always distribute the same way. So what are our rules gonna be when we're distributing? This isn't like a must-do rule, but it's a recommended rule.
Left or right?
You could, but what I would say instead is I would say my bias is I'm always gonna distribute from the polynomial with fewer terms to the polynomial with more terms, because then you actually have to do fewer rows of distribution, and you'll see what I mean by that. Okay. So in this case, like over here, it wouldn't make sense for us to distribute the 3x and then distribute the 11. It would make sense for us to distribute the negative 2x to both of those, right? If we look at another example up here where we've got, well, they don't give us, how about this one? Like this one right here. It would make sense for us to distribute the w and the negative 7, because then I'm only having to distribute 2 things instead of having to distribute 3.
Oh, look at that.
You see what I'm saying?
Yeah.
And there, you may think, well, it's the same number of total distributions. It is, but when I start to show you some tricks for keeping this organized, you'll see why that's a little bit better. Okay? In fact, you know what? Let's do that one first. Yeah, I think that's a good idea. This is a good one to do first.
I remember this one, like we had one, a really long polynomial
Yeah.
Good story.
And I'm the only one who got it right.
I'm not gonna give you any really, really long ones to do with this, just because they take forever and it's easy to make a little mistake, and you pretty much know how to do it, right? I'll give you, like, the biggest I'll probably give you is a 3x3. Okay? To do.
What? Like 3 and 3.
No.
No, like 3 different like numbers. Yeah, 3 numbers. Yeah.
Come on, Jake.
That's kind of hard for my brain.
Okay, so let's take a look at this one, and I want to make a point here. So if I distribute this, what would you do?
W minus 7.
Okay, so let's do that. I'm going to distribute the W. That'll be our blue distribution. So that's going to equal
W cubed plus W plus W.
Then I'll distribute the negative 7s. What's that going to give us?
Negative 7 W minus 14 W minus 7.
Okay, that's fine. But do you see that if I were multiplying out some big polynomials, I'm going to get like lots and lots of terms to add, right?
Yeah.
It's easy to, it's confusing. If I have a long string of terms, it's kind of hard to keep track of which ones go together, right? So there's a better way to do this. When we do our distribution, let's do it this way. I know what's the degree of this polynomial going to be when we're all done.
3.
It's going to be cubed. How'd you get that?
Because the largest is.
Oh, okay, good. Because if I take the degree of each polynomial, I could add up those degrees, because the biggest power I'm going to get of w's is always going to be when I take the leading term times the leading term, right? So a first degree times a second degree is going to give me a third degree, right? Okay, so then when I make this distribution, I always want these to start off in standard form. I'm going to get my w cubed plus 2w squared plus w. But let's make sure when we do this, we can use what's called like a tabular method for adding up these terms. I can set these things up in columns. Let's always have a column for every power of the variable, right? So for example, what if this was a w cubed? And when I distributed the w, I would have gotten w to the 4th plus 2w squared plus w. Then I would leave a column for w cubes, even though one didn't show up. How come? Because I might get one later, right? And so when I distribute... Hey, what's up? Okay, let's get back on track though. Okay, so here's the deal. Hey, too much talking. Up here. Hang on. So when we distribute the 7 then, the negative 7, here's what we're going to do. Every time we make a distribution, we're going to go to a new row, right? So when I distribute the negative 7, I get negative 7w squared. Well, that goes in this row.
Oh.
Negative 7 times 2w is a negative 14w, and negative 7 times 1 is negative 7. And then all I have to do, if I leave a column for every power of the variable, I can just add these things up vertically, and they're already all lined up, so the like terms go together, right? That's really handy if you have, like, what if I had a trinomial times a polynomial? Then I'm going to get 3 rows, and that's going to be a total of 12 terms, right? So, okay, so here we go. If I add all these up, I'm going to get w cubed, minus 5. All I got to do is add the numbers up, right? Negative 5w squares. To my w's, I get negative 13 and a minus 7. Easy, right? Good little trick, okay? So then what about something, we don't have to even do this whole one. How is this going to go down when I do it, though? What am I going to get from this first product? What's the degree of the polynomial I'm going to get?
Squared.
Okay, good. I'm going to get a quadratic, aren't I? I'm going to get a quadratic polynomial and a quadratic polynomial, and then all I'm gonna do is just subtract those polynomials.
Yes.
Hey, look, I got a little too much chatter going on.
Wait,
Question?
do you distribute the 2x and then subtract h2, or do you just?
You would. So we're gonna, and the point I wanna make here, and I won't even take you through all the steps. We can just kind of talk through how it's gonna look. How do we determine what the order of things I do is?
PEMDAS.
PEMDAS, right? We're simplifying. We're not solving or isolating, we're just simplifying. We multiply stuff out, right? So we're just gonna do this. We go back to this all the time, it's PEMDAS. So inside parentheses, there's nothing I can do, right? There's no like terms to add. There are no exponents, but I'm gonna multiply from left to right. So the first thing I'm gonna do is I'm gonna have to figure out what's that product. So I'm multiplying there, and here's another product, so I'm multiplying there, right? And I'm gonna simplify those. I'm gonna multiply and collect like terms. So that's my first step, and then my second step is I'll just add up like terms. Distribute the negative 2x, right? I'm just gonna add up all the like terms.
Yes.
So there's step 1, step 2. Step 2 would be add all that stuff up, right? Okay, what do we do with something like, how about this guy?
Which one?
Okay, say that again, Gabe?
You do it once, then again.
Good, we do it once and then again. Now we're gonna come up with some patterns for expanding binomials like this, but we're not there yet. So for now, all we would do on this guy, until we get a better way of doing it, right, so all I'm gonna do, if I wanna cube something out for this point, right, later on, like I say, we'll have a better way of doing this, but for now, we would just write this out as 2c plus 5d times 2c plus 5d times 2c plus 5d, right? And then we would multiply that out, get an answer, and then once I get that, I'm going to multiply that out, right? Keeping in mind that I multiply in pairs. Don't make the mistake of trying to double distribute. It's not like I'm going to distribute that 2c there and there. I don't do that. I only can multiply things in pairs. If I multiply the numbers 2 times 3 times 4, I go back to this example all the time because it's so simple. I don't distribute the 2 to both the 3 and the 4. I multiply 2 times 3, simplify, get an answer, and then multiply that result times 4. Same thing here, okay? All right. So we could do, I'm not even going to take you through one of these. You could do these, they're just time consuming. For this level of class, I don't think we need to do a big example like that. Okay, here's the last thing though, dividing by monomials. Last thing we want to do. Okay, so if I'm dividing a polynomial by a monomial, it's easy to do. All I have to do is just split this up. That's like a common denominator, isn't it, if I have a monomial on the bottom? So I'm just going to split this, and the way we'd say this, we're going to split this and divide term by term. So for example, let's take this guy right here. Okay, what would I do? I'm just going to break it up into separate parts. I'm just going to break it up into 20x cubed divided by 4x minus 4x squared divided by 4x minus 8x divided by 4x, right? And I can simplify each one of those. What's 20x cubed divided by 4x? 5x squared, good, right? Because I got like bases, so I subtract exponents. What's 4x squared divided by 4x? X, good. And then 8x divided by 4x? Easy, right? Let's maybe do one, how about if we do one involving multiple variables? Let's do this one. Okay, so we can probably do that without having to write it out. We could just do this in our heads a little bit, right? We're gonna divide each term by the denominator. So what are we gonna get for our first term? 30 over 12. 15 over 6. I can go one more than that.
5 over 2. Yeah, 5 over 2.
5 over 2, there we go. So I get 5 on the top. I'm getting 2 on the bottom. And then c to the 8th over c squared. C to the 6th. D cubed divided by d. D squared, good. So I'm getting minus 36 over 12. So I got a 3 on the bottom, right? C to the 6th over c squared.
Straight through, but yeah, so.
Oh, sorry, 3, not 1/3. What am I doing? Okay, so I'm not even going to put a bar yet, right? Because I may not end up with any variables on the bottom. In fact, do I?
No.
Right, so I don't even need to put that 1 on the bottom. So I get 3c to the 4th d plus 6 over 12 reduces to 1 over 2, good. And then I'm going to get c cubed over c, d over d, cancels vertically, right? So that'd be my answer. Okay? Okay, yeah.